you right now. Did you hear it? Did you hear it?
When you see cochlear implant patients one by one, when you see the child born deaf develop remarkably normally.
The cochlear implant is the first substantial restoration of a human sense using a medical intervention.
The ability of the human auditory system to separate the signals that it wants from the signals that it doesn't want is almost miraculous. And to approximate that using software algorithms and then interface the output of the program to the human cochlea is revolutionary and remarkable.
These are people who have had an idea and even in the face of significant barriers have actually taken that idea and turned it into something that not only improves the human condition but is commercially successful.
The implant is surgically placed under the skin. An audio processor behind the ear takes in analog sound information, processes it into digital signals, and transmits them via a coil to the implant in the inner ear. Here we see a schematic of the cochlea. And here are the hair cells. They bring the sound event to the nerve fibers. And these nerve fibers send this information onto the brain, which creates a sound impression. For the deaf, these hair cells don't work. The cochlear implant takes over this function and transmits the sound signals directly to the auditory nerve. There they are perceived as acoustic signals.
So the whole series of engineering issues that had to be addressed that related to the accurate controlled translation of information about sound, you could say, to pattern stimulation of the auditory nerve. We solved those issues one by one in ways that led to the creation of a model of a practical multi-channel cochlear implant.
The challenge was to put a wire around that, and I got the idea from a shell and found that the wire would go in if it was bent and flexible. That then led us to designing the first prototype.
Our contribution was the design of a multi-channel microelectronic cochlear implant, which is the prototype of presently available implants. And we also designed the electrode, which is inserted into the scalar tympani.
The electrode arrays had been developed before we came along, principally by the other winners of the Russ Prize, and we discovered new ways to utilize those electrodes more effectively, such that most persons using cochlear implants could understand conversational speech with hearing alone and without the aid of lip reading or other visual aids.
The cochlear implant represents a kind of modern miracle. Someone that can't hear, as a consequence of the application of sophisticated modern engineering, can hear.
Then came the moment of truth when we switched him on for the first time.
And I was, no. And then Richard kept going. And then that big second I heard a dong. I sort of went, oh, no, that. It was after 17 years profoundly deaf. And getting that sound back again, I was in heaven.
Oh, for me, it's a wish come true, really. I always wanted to work in biomedical engineering, and not only to come up with something, but to have that delivered to lots of people such that they can profit from it in their daily life. And I could not imagine any better example of bioengineering than the cochlear implant, really.
But it's extremely motivating to see these little children grow up with the cochlear implant and leading a normal life.
The fact that it transforms people's lives and gives many deaf children near normal spoken language is the greatest personal reward.
Well, the cochlear implant is a transformative technology that allows children to enter mainstream schools, for adults to have a wide range of job opportunities, and for all recipients to connect in new and important ways with their families, their workmates, and society at large.
This technology has been used to enhance and improve the lives of hundreds of thousands of people and enable them to be more productive and have more fulfilling lives in a variety of ways. The cochlear implant is almost the definition of create for good.
There are two meanings of the phrase create for good, and one is to do the right thing. And I think we're talking about improving the human condition and rewarding that with the Russ Prize. And that's one part of the good. And then the other part is that it really has to have had widespread impact. And to me, that means widespread impact for a significant period of time. I firmly believe that what the Russ Prize means to the world now is exactly what Fritz Russ wanted it to mean. He wanted to be able to recognize engineering achievements in the same way that the Nobel Prize Committee recognized achievements in economics, physiology, literature, and so on. And so that really was what started him thinking about the Russ Prize. And according to him, he thought about the Russ Prize back in the 60s. Now, this was long before he was even capable of thinking about setting up the Russ Prize from a monetary point of view. But he then decided this really, at least at first, needed to be associated with bioengineering. Bioengineering was a fledgling field that Fritz believed needed to be encouraged. Examples of past winners of the Russ Prize have included inventors of the implantable heart pacemaker, the inventor of kidney dialysis, the inventor of the automated DNA sequencer, the inventor of the enabling technology for heart-lung machines, the blood oxygen sensor, the inventors of the technology behind LASIK and PRK eye surgery. I think the reason Fritz wanted the Russ Prize recipients to come and visit campus is so that they could inspire our students. Russ College students and faculty have been able to significantly interact with almost all of the Russ Prize winners. Our students being able to talk to these people lets our students know that they can also do these things. And they can also observe the characteristics of these people who've been successful in improving the human condition with an achievement that's in widespread use.
It's a wonderful human thing to have contributed to. It is, in fact, the stuff of miracles.